Dr. Zucker presents My Magic Squares, an algorithm using antisystem approach.
This video consists of two parts. Part 1. Short historical overview of known magic squares. Part 2. The anti-system algorithm of Dr. Zucker for design of magic squares.
The first magic square was created in China in 2000 BC and is called Lushu Square. The square has dimensions 3 by 3 and consists of adjacent numbers from 1 to 9.
The similar magic square with the same sum of 15 was published 1750 by the German poet Johann Wolfgang von Goethe in the 1th edition of his work Faust. This square is non-classic because the numbers are not neighboring and is incomplete because of the sums along one main diagonal. However, mathematics meets art.
Leonhard Euler proposed rules in 17th century how to build the magic square using two squares, one filled with Latin letters and the other with Greek letters, which were overlapped. Such squares are known as Latin-Greek squares. They have the same sum in each row and column, but not in main diagonals. To get the same sum in main diagonals, the following conditions should be fulfilled.
Another example of non-classic magic square of fourth order with a sum of 224 in each row, column and main diagonals, is shown below. However, the square is overdimensional because of the many new features.
The first classic overdimensional magic square with neighboring numbers from 1 till 16 originated from Indian village Khajuraho in 11th century. The same sum of 34 is achieved not only in each row, column and main diagonals, but in much more squares and other figures.
This magic square, originated in India 2000 years ago, is pan-diagonal because besides having equal sums in each row, column and main diagonals, it also has equal sums of the second and third order, along the paths of the inner square ABD in the following way.
Th5 magic square of India fascinated the German painter Albert Dürer. He modified it with the same sum and showed it in 1514 in his copper engraving Melancholia. Again, mathematics meets art.
If we swap the rows of the pan-diagonal magic square, shown on the left, then we get an incomplete magic square that loses equality of sums along diagonals.
The Dr. Theophrastus Bombast von Hohenheim, known as Paracelsus 1493–1541, was one of Martin Luther's contemporaries. His magic square of the fifth order belongs to classic squares with neighboring numbers from 1 till 25. The special feature of this square with the sum 65 is that one of the main diagonals is formed from the consecutive natural numbers from 11 to 15. Also, two partial diagonals, namely 7, 8, 9 and 17, 18, 19, are series of natural numbers, although the sum of these numbers is not 65.
In this 8th order magic square, the sum 260 is found only in rows, columns, but not in main diagonals. However, this square is one of the overdimensional ones because, on the one hand, each half row and half column has the half sum of 130. On the other hand, the magic sum 260 also results along several paths, which are created according to certain templates from 16 individual boxes.
The supermagic square of Benjamin Franklin. The next example, the 16th order square, was also developed by Benjamin Franklin and belongs to the class of complete overdimensional squares. In this square the sums 2056 are not only found in rows, columns and in main diagonals, but also within a windows that consists of 4 by 4 individual boxes. 2 of them are shown below as examples.
With the supermagic square of Benjamin Franklin, we finish the overview of sum squares and go to magic product squares. The magic product squares are numbers arranged in such a way that the products in every column, in every row and in the two corner diagonals equal to the same value. The sum squares can be formed according to strict methods, but also by trial and error. On the other hand, magic product squares can only be constructed using mathematical methods. The simplest method is the power method, in which the numbers of a sum square are expressed as exponents of the same base, e.g., of the base 2 as shown below for product 32,768.
Another method of forming product squares is developed by Leonhard Euler in 17th century. Two squares, one filled with Latin letters and the other with Greek letters, are overlapped. Such squares are known as Latin-Greek squares or orthogonal squares. They have the same products p in each row and column. However, it is clearly seen that the products of main diagonals differ from this product. The following condition between Latin and Greek numbers should be fulfilled to get the equality of diagonals. To satisfy this condition, let us take, for example, the values of a, b, alpha and gamma. Then follows the template. Examples.
Latin-Greek magic product square, fourth order of Leonhard Euler. After overlapping of two squares, one filled with Latin letters and the other with Greek letters, arises the magic square with the same products p in every column, in every row and in the two corner diagonals. It is the overdimensional magic square because of the equality of products p in many big and small squares.
The term antisystem was known since Newton's law of motion.
For every action, there is an equal and opposite reaction.
Dr. Zucker applied in 1983 this conception for automation control. Let us see a simple system with two inputs x1, x2 and two outputs y1, y2.
For every dynamic system with an operator A with inputs x1 and x2, there is an equal and opposite reacting system, with the same operator A with inputs z1 and z2. Significant is that between system and antisystem, there is the intensity balance E1 equals E2 by any values of z1 and z2.
First of all, let us build a 3 by 3 square. The desired value of beta we put in the middle. Then we represent the square as a system with the input 3 beta and the anti-system with the input 2 beta, considering conditions for y1, y2 and y3. That's all. The magic will take place according to the anti-system approach. The resulting magic sum square, according to the anti-system algorithm, is shown below. The value of beta should be given, or will be chosen averse. The values of x1, x2 and x3 will be chosen arbitrary. However, they should satisfy the following conditions. Example 2. Let us rebuild the famous Lu-Shu magic square upon anti-system method. Example 3. The desired value beta is equal 6. Let us once more build the magic sum square upon anti-system method. Note please that the magic squares have not only the same sum of free beta in each row, column and main diagonals, but also the sum in the big and small diagonal squares are equal.
The magic product squares are numbers arranged in such a way that the products in every column, in every row, and in the two corner diagonals equal to the same value. Let us build the 3x3 magic product square with numbers x1, x2, x3 as the system with operators a1 and a2, and numbers y1, y2, y3 as the anti-system with operators b1 and b2. The numbers alpha, beta and gamma will follow as balance between system and anti-system. Template of magic product squares third order in the example.
Example. Birthday magic product square. Supposing you want to create the magic product square to your birthday or birthday of your friends. Put your age beta in the middle cell. Further choose the values of x1 and a1. Then you will get the magic square shown on the right.
Anti-system approach for magic product squares fourth order. There are two systems and appropriated two anti-systems. The template for calculation of magic squares is shown in next page without explanation. For more info see my book Existentionale Mathematik. Template for calculation of magic squares and examples. Finally, let us build a magic product square using template of anti-system algorithm and compare it with the Latin-Greek square of Leonhard Euler as multiplication of two squares. Both methods lead to the same magic square. Thank you for attention. Goodbye.